Welcome back, guys. So in the previous lecture, we have implemented user-defined functions in the view of the def keyword, which is a function declaration. And we've been talking also about lambda functions, which are the anonymous functions, and which is the best use case for passing such functions as callback functions, for example. So today's lecture is divided specifically for the lambda expressions, that is, two lambda functions. And let's just start writing directly from the test. I'm writing the lambda function test.js. And let's write the following expression. Let's define the function onClick, which is the event handler in UI programming for different components, and which accepts the callback function, right, as the parameter. As the body of the function, let's do just simple expressions, variable x, y, and the result of the onClick function is the result of calling callback function. Okay, and then let's call the onClick function. That is, let's activate this event handler, and with passing the callback as the lambda function. This will be our new expression, lambda, which is the same as the function declaration has the parameters, list of parameters. In this case, we have only one parameter, data, and the function body, right, and data times 10. So as the result of this calculation, we should see x plus 1030 times 10, 300. Okay, let's execute. And yes, we predictably see lambda is not defined. Let's go ahead and implement it. So what is lambda? As we said, it's just a function which doesn't have a name. It's an anonymous function expression. And our interpreter can already define functions, right? This is exactly the behavior of the def keyword. And in contrast with the def keyword, we just create the function and directly return it without installing into the environment under the function name, and simply because lambda function doesn't have a name. So as you can see, we extract parameters and the body and just directly return the same closure objects, which encapsulates parameters, body, and the captured environment. And that's pretty much it. There's no any magic behind the lambda expressions. Again, these are just functions without a name. Let's go ahead and execute, and yes, all assertions passed. So again, what's happened is we created the function object, that is the lambda, and assigned it to the variable callback, to the parameter callback. And in fact, it's exactly the same semantics as having the function declaration. And in this case, we just manually attached the function to the explicit name callback. And then when we access the callback variable, it's determined as the function object, right? The variable lookup returns the function object, and we can call it. However, as we said, lambda functions do not need a name, and we can just create a function and directly, that is, immediately apply it right away. And we call such expressions as immediately invoked lambda expressions, or for short, ILI. So let's take a look at this example. Okay, so we create a lambda function which directly corresponds to the square implementation we had previously. But in this case, we don't have a name for this function. And we immediately apply it to the value 2. So as the result of this calculation, we should see the value 4. And this is exactly the same as we first define a function square and then call it by name. Okay, let's execute. And yes, it works. All assertions passed. Again, this works because our call expression, that is function call, calls eval on the function object, right, on the first function name. And in this case, it's not the name of a function, but directly the function object itself. So eval will be applied on the lambda. The lambda is created, and we immediately execute it to the value 2. Finally, the same as we did when we passed the callback as the parameter, we can actually just save a lambda function into a variable, right? For example, we can use a variable square, which is assigned to the lambda function. And since our variable declaration expression installs a value into an environment, we are able to call it by the same function square. Okay, let's execute, and yes, it works. Now, this expression is very important because it shows that function declaration, right, the def keyword which we have, is nothing but a syntactic sugar for a variable declaration installed to the lambda function, right? And this is the first step when we start talking about syntactic sugar and just-in-time translation of some expressions into equivalent alternative expressions. So let's see how it works. Okay, so we come back to our function declaration, that is the def, and tell that this is nothing but a syntactic sugar for a variable declaration assigned to a lambda. Again, we extract the same name, parameters, and the body, and then just gtranspile to a variable declaration. What this means, we create a variable expression node directly at runtime. And as we can see, we create the var keyword with the same name, with the function name, and then just create a lambda expression, passing the same parameters and the same body. And then we just delegate to the variable declaration evaluator, which will create a variable and install it to the lambda. That's pretty much it. And again, this is the first precedence. We'll be using the syntactic sugar, and we actually will have a separate lecture for the different syntactic sugar notation. And later we'll refactor this transform module into a separate class. So we'll be able to either call it just in time, as in this case, or at runtime. All right, so let's make sure our function declaration still works. That is the def keyword. And yes, all assertions passed. Okay, so congratulations. We now have a very powerful abstraction called lambda functions, which are the most convenient passing as callbacks and doing some immediate calls to set up local scopes. And in the next lecture, we'll continue again talking about syntactic sugar, and we'll implement several more expressions, for example, for loop, switch expression, etc. That's it for today. Thanks, and see you in the class.